Hello everyone, I'm Simon Parkinson from Huddersfield University. So I'd just like to say that this work is in collaboration with Peter Gregory over at Teesside. So first of all, I'd just like to give you a little bit of an introduction of what machine tools actually are, for those who don't know. So a machine tool is something, it's a subtractive machining device, which they're used in pretty much making everything, to be honest. So on the left there, you can see that they're used for some dental implants in the medical industry. Then on the right there, we're using them in aerospace for machine wings. So there's a whole range of different machine tools out there, and while there are a few ready available pre-selected machine tools, if you like, a lot of them are configured to the client's needs, and they're optimized in terms of size, material, and power. So the demand, especially in the UK, we're moving towards a more advanced manufacturing goal, where we're trying to make things that are probably more profitable. So we need machine tools that can do this and can cater for this requirement. So really what we want to do is we want to either make companies that have got machines want to improve them so they can move into the new manufacturing sectors, or if they've got their machines to maintain the accuracy of them. And in general, increased accuracy is increased cost. So here's just an example of a German machine which has a very large working volume, but it's got an accuracy and repeatability of only 20 microns. And just to put that into perspective, 20 micron, the average human hair is 70 microns. So you can imagine how difficult it is to move so much weight and position it with such accuracy. So all machines have errors. As they move, they have geometric errors, thermal errors, dynamic errors, and this results in deviation from the expected position, the actual position to an expected position. So to understand this deviation, we perform something called calibration or error mapping, where we analyse the machine's behaviour using a set of predetermined tests, and then we can do things like compensation or other mechanical corrective devices, if you like, to fix the machines. So what complicates the process of machine tool calibration? Well, there's a strong temporal desire on reducing downtime. People who have the machines, they want to be able to use them as much as possible. So trying to get them to take the machine out of action for 2 days can have significant costs for them. And then obviously there's the measurement quality. They want to make sure that when they measure the machine, they're getting the best possible result out of it. And many factors influence this. So just down at the bottom there, I'm just showing the geometric errors of a linear axis and a rotary axis of a machine tool. So typically a machine tool will have three or five axes, 3 linear or 3 linear plus 2 rotary. And all the error components of each axis get measured individually. So just a little bit on the temporal aspects there. So when they set up these instruments to measure these errors, there's loads of different instrumentation you can use, but each one will take different time to set up, different time to measure, and then different time to remove. But in some cases, you can optimize because the same equipment can be used to measure different errors. So on the bottom left there, you can see a Renishaw XL80 laser interferometer, which is set up to measure positional deviation as the machine moves. But by just changing the optics of the laser, you can easily measure for straightness and angular deviation as you move. So temporal optimization. This can be achieved by selecting equipment, providing that it can satisfy the requirements. So it's okay saying that I'll use this piece of instrumentation for every measurement. But if it can't meet the criteria the manufacturer wants, then it's not viable. And then sequencing the measurements so they use the same instrumentation. So like I was saying about the laser on the linear axis, you'd want to sequence them all together if possible so you're not setting the laser up to measure one error and then taking it away from the machine, doing something else and bringing it back, so that just doesn't make sense. And if possible, perform concurrent measurements. So some previous work we did back in ICAPS 2012, where we had this temporal optimization model, we could produce calibration plans which resulted in about an 11% reduction in downtime based on 12 machines we tested it on. So that was good. But now we want to optimize, in addition to time, for also the uncertainty of measurement. So the uncertainty of measurement, it's the quantification of the doubt regarding the measurement. So for example, there we have a ruler Now let's say we're measuring 20 millimetres on that ruler, but it's actually 20 plus or minus 1 millimetre. All measurements have a standard uncertainty. If anything you buy, if you buy, I don't know, coffee, ground coffee on the back, it'll say, I don't know, 20 grams, and then it might have a plus or minus 2, or it might just have an E symbol to say it's estimated. But why is it important for machine tools? So during calibration, errors that are out of tolerance could become intolerance just because of the estimated uncertainty. And similarly, it'll affect the manufactured parts of the machine, because if the machine's errors have been passed off to be within tolerance, but they're actually not because of the uncertainty, then everything made on the machine could also be out of tolerance. So just a little example here. So here we can see the conformance zone in the middle is where if you were to measure any measurement with a ruler and say we have a tolerance of 2 millimetre there, whereas 20 millimetre 2 millimetre tolerance. So anywhere in that conformance zone, the measurement will be passed off as fine. But then if we were to measure, say, 22 millimetres and we had a plus or minus 0.1 uncertainty, then really it could go either way. We could be falsely accepting the error, or we could be falsely rejecting the error. So it's really important to minimise these tolerance windows, if you like, to remove incorrect decisions. So what can affect this tolerance window? So one of the main ones within the machine tool environment is the environmental temperature. Some of the factories that one of our clients works in China, their environmental temperature changes on about a 20 degrees centigrade scale every day, and this causes massive problems for their machines. So as you can see over on the right there, we've got just a simple picture of how the temperature will adjust or deviate the machine's structure and result in positional deviation. And just on the bottom there, we've got a little graph, a little example of the same error component measured at two different temperatures. And the temperature, I think there was 5 degrees C difference between the two temperatures, but the error increased by 2.5. So how can we optimize our measurements based on the temperature? So first of all, we took our temporal model and we extended it to include for this. So if we look at the bottom graph there, what we really want to do is as the temperature is going up and down, I should point out that calibration will take place over a few days. It's not just a 1 hour job, it's quite a long period. So in them few days, the temperature will go up and down, obviously. So the idea would be the ideal would be to schedule measurements where the temperature difference throughout the measurement is at its lowest. And also, when you've got the kinematic chain of the machine, any error that propagates through it, you want to make sure that when you're measuring them as close together when the temperature is at its most stable, so that the uncertainty is reduced. So our domain is a PDL 2.1 domain, and it has 5 actions, and we take the view of accounting for it in the instrumentation's point of view. So what are we doing with the instrument at the time? So it can be set up, it can be measured, adjusted and removed. Now we've got 2 measures there because one of them accounts for where we've got multiple measurements where the uncertainty propagates through them, and one of them is just where there's no propagation. So to get our temperature profile into our PDL domain, we needed to remove the continuous factor as much as possible. So we discretized it based on the sensitivity of the instrumentation and the machine tool. So here we've just got the historic data for 48 hours, and you can see how it deviates from 20 degrees C. 20 degrees C is the standard in the ISOs for machine tool measurements. That's why we're deviating from 20 degrees C. So we represented these as a series of durative clips, durative actions just clipped together. So you can see that from 0 to 42 in the Makespan, the temperature will increase at 0.005 per time unit. So using this, it allows us to have the temperature at the start of a measurement, or the rate of change, if you like, at the start of the measurement, the rate of change at the end, and then we can calculate how it changes throughout the measurement. Right, so how do we calculate the estimated uncertainty? So there's a lot of contributors which just get summed together, and then we do the root sum of squares on them to get the estimated uncertainty. Now, we're only looking at temperature-related ones. Now, there's a lot that could be looked at, but just for this presentation, for our model, we're just looking at the uncertainty due to the change of the machine tool temperature. So you can see it's relatively straightforward to calculate that. and the values are all predetermined, so the length of the measurement we're taking, the error range of the machine, so it's all easily encodable. So you can just see there, in our PDL measure action, you can see how we do that there. Right, so some experimental analysis. So we used LPGTD for our domain, with our 10 minutes of CPU time and 4 gigabytes of RAM, and we optimized for 3 different metrics. So we went for Makespan, the cumulative uncertainty, and then Makespan and cumulative uncertainty. Now we just used a standard deviation for now, but it could easily be weighted for if, say, the manufacturer wanted a higher emphasis on uncertainty, if they had more time, perhaps. So here's just an example of a little bit of the uncertainty plan. So you can see on the bottom there we've got the measurements, the blocks, and the red line is the temperature change throughout that section. Now you can see that the temperature variation is low when we're optimizing for uncertainty, but the actual downtime induced to the machine tool from using this calibration plan was 1 hour higher than when optimizing for the Makespan. But it resulted in a good reduction in the insertive measurement. So how about when we try to do both, a standard deviation of both metrics? So we can see that we got an uncertainty of 28 microns, and we did the maximum just for a good difference there. Now you can see on this one it's quite interesting. You can see how some measurements have been scheduled in the middle, which use the same instrumentation, so the instrumentation doesn't have to be removed and reset up again, so that reduces the downtime. And then you can also see how some of the measurements where uncertainty propagates through are scheduled where the temperature variation is not the best, but it's okay. It would be better to have it further on where it's lower, but it's put it in that spot. So it shows a good compromise. And so we did this for 12 different calibration instances, and you can see there that we've got the optimization metric time, uncertainty, and then time and uncertainty. So you can get from that a good feel for how it's performing, and this has received some good feedback from our industrial partners, because currently calibration plans are just done by domain experts, and they'll often just do them ad hoc. There's not much structure. But allowing a tool like this for them is proven a significant benefit. So in our paper, we've established that it's possible to create these valid calibration plans, optimize for time, optimize for uncertainty, and then do some multi-objective optimization, which is on average 9% worse than the best known solution when doing the single metric optimization. Now, for future work, we want to make this tool more accessible. At the moment, we're just using PDL models, and we want to embed it in some software tool for the engineers to use. And there are many other factors that we need to consider for the estimated uncertainty, although temperature is the main one, and the main one that our industrial clients are interested in. But it would be interesting or beneficial for other measurement people, if you like, in the measurement disciplines, if we could include more. So thank you for listening. Any questions? Probably finished a bit ahead of time there. So
we do have a good amount of time for questions. Yeah. Actually, Drew, go ahead.
Maybe you answered it with the last slide there, but do people find it difficult to follow these plans, or easy, or how does that work exactly?
Well, we've done some case studies. It's not actually been released into industry. It's just been they've done the case study on an industrial machine with a partnership with the university, and the plans are they find them easy to follow. But the problem is if something's wrong, then they have to go back and regenerate the plan.
Thanks for the talk. So you're using LPG, and you've got the same model. You're changing the metric. Mm-hmm. Do you have a handle for how sensitive the performance of the planner is to the metric you put in the problem file?
A little bit. It does. In terms of time to get a valid plan, it is longer when trying to solve for the multi-objective for both of them. but it is the only planner that we seem to be able to get to do it for us. But yeah, it does seem to slow it down. That's,
Any other questions? So I have one question. Can you actually go back to your
sure.
results slide with the bar graph?
This one, yeah.
Yeah. So I note that when you're optimizing for uncertainty, your time is actually pretty good from when you optimize for uncertainty in time. Can you talk about that a little bit?
well, not really quite sure as to why, but yeah, no, it is.
Okay. Yeah.